Hello, everybody, and welcome to the lecture for Thursday of week 13. So today we're going to talk about rational approximation and Pell's equations. So just to recall where we're at, so last time we looked at equations, the form x squared minus dy squared is equal to 1. So in particular, we looked at the case where d here was 2, but more generally, we can look at whenever d is a square-free positive integer. Square-free positive integer. And these equations are called Pell's equations. And the main thing we saw is that once we have one solution, then we can produce many more by using arithmetic in sort of the ring of quadratic integers. If we have a solution x1, y1 to this equation, well, it's the same as giving an element x1 plus y1 squared root of d with the norm of this equal to 1. So we this element x1 plus y1 squared root of d has norm 1, and so the norm of this to the kth power is equal to the norm to the kth power is 1. But on the other hand, if I just expand this out, I get some xk plus yk squared root of d, and so that tells me that the norm of this is equal to 1. So it gives you another solution of this x squared minus dy squared is equal to 1. So that was the main thing we saw, and we applied that to classify square triangular numbers. And then, so that was with d equals 2. And then on the worksheet, the first exercise that we went through most of on Tuesday, you were working towards classifying square pentagonal numbers, which used d equals 6. Okay, so here's a fact that I said last time, but let me say it again. If x1, y1 is the smallest positive integer solution, so what do I mean by smallest? Well, I just mean the x coordinate is either, like the x coordinate is the smallest of all positive, of all x coordinates of positive integer solutions, or the y coordinate is the smallest. So this is sort of, you can look at the x coordinate or y coordinate equivalently, because x squared is equal to 1 plus dy squared. So somehow as x gets bigger, y also gets bigger, and vice versa. So it doesn't sort of matter whether you talk about the one with the smallest x coordinate or the smallest y coordinate. Okay, so if this is the smallest positive integer solution, then in fact all other positive integer solutions can be gotten this way. So if you want to get sort of all of the solutions to Pell's equation, all the positive integer solutions, you sort of start with the smallest one, and then you sort of do this process to make new ones, and that really gives you all of them. Like what we did last time was we saw d equals 2. When d equals 2, then the smallest positive integer solution was 3, 2. So that sort of corresponded to 1 being a square triangular number. And then we sort of raise this to the power to compute the other square triangular numbers. So we didn't justify this fact yesterday, and we're not going to, or on Tuesday, we're not going to justify it today either. But I do want to say a little bit about how you would do this. So say you had some other solution, x plus y squared root of d, where x and y were positive integers, and you want to show it with some power of the smallest solution, so you have this x1, y1. Well, you just take it, and then you just try dividing it by x1 plus y1 squared root of d. Now, since this element has norm 1, so dividing it by it is the same as just multiplying by x1 minus y1 squared root of d. So when the norm is 1, sort of division is the same as sort of multiplying by sort of like this conjugate, where you sort of replace square root of d with minus square root of d. So this looks a lot like things we're doing in the Gaussian integers. The same holds here. And then if you expand this out, you get sort of x times x1 minus d times y1 plus x1y minus x1y1. So this is sort of something, this number is definitely smaller than x, because you're subtracting off something positive. So somehow if you can show that this thing you get is a positive number, or sorry, if you can show this thing you get is a positive integer, then you can sort of just keep on repeating this process until you get down to the smallest one. You sort of just can keep on repeating this division, and eventually you'll get down to the smallest one. And then sort of, if you sort of undo that, you'll see that the thing you started with had to be a power of the smallest solution. but so, okay, so like then the subtle part is to explain sort of why this number and this number, why these are both positive numbers. And to do that, you need to think a little bit and maybe draw a little picture. It's not too bad, but I don't want to get into it here. So if you want to see, if you want to see how to argue that these are positive, you can look in the book. This is theorem 43 on page 129. So what I want to focus on instead today is another part of this statement, which is, well, I said once you sort of once you have the smallest solution, you take all other solutions are given by powers. But actually, if I just sort of write down this Pell's equation, like this x squared minus dy squared is equal to 1, then I don't know whether that has any solutions at all. So to talk about with positive or integer coefficients, so I don't know that I can find x and y positive integers such that this holds. I mean, you really have to sort of justify this statement. And you can't talk about the smallest positive integer. So you can't talk about the smallest solution, the smallest positive integer solution, until you know that there's at least one positive integer solution. So what I want to talk about today is sort of how you can sort of show that there really is always at least one positive integer solution to Pell's equation. So this x squared minus y squared d is equal to 1. Okay, so here's a key observation. It says sort of we can relate sort of solving Pell's equation to another type of problem, that of sort of approximating the square root of d by a rational number. So let me just explain how that works. So say we have sort of some solution where x and y are positive integers to x squared minus dy squared is equal to 1. Well, let me just rewrite this as the norm of the element x plus d square root of d times y, which is just x plus square root of d times y times x minus square root of d times y. I get that's equal to 1. And so in particular, x minus the square root of d times y is 1 over x plus the square root of d times y. Okay, so if I take the absolute value, like if I ask how big these numbers are, well, this actually tells you that this number on the left is pretty small. Because, well, if I just look over here, 1 over x plus square root of d times y, I mean, x, y, these are both positive numbers, square root of d is positive number, so this is less than, let's say 1 over y, just to get an estimate. And so, in particular, sort of this thing on the left, which is equal to this, so x minus square root of d times y is less than 1 over y. Now, if I sort of divide both sides by y, I get sort of x over y minus square root of d is less than 1 over y squared. So somehow, if y is big, then sort of 1 over y squared is very, very small. And so that's telling you sort of x over y is a pretty good approximation of square root of d. So this sort of says x over y is a fraction that gives a good, so that's sort of, let's say, approximates square root of d pretty well. So somehow solving Pell's equation is actually related to this problem of how can we approximate irrational numbers using rational numbers? How can we approximate the square root of something that's not a square using a rational number? Okay, so just an example of what this looks like in practice. So if I look at this sort of solution we talked about for Tuesday, to the Pell's equation with d equals 2, and I get 99 squared minus 2 times 70 squared is equal to 1. So 99 and 70 is the solution. So x is 99 and y is 70. So if I look at the fraction 99 over 70, and I just sort of expand that out by Google or whatever, I get 1.4142. And then I think the next thing is maybe 8. I didn't write it down here, but there's things. And then so the next term is not 1. But if I look at square root of 2, I get 1.4142. So these agree to the first 4 decimal places. So that means this number 99 over 70, like it approximates the square root of 2 up to sort of up to 1/10,000th. So that's pretty good. It's even better than this naive than this estimate gives. So this estimate would say that it was going to approximate it to 1 over 70 squared. We do it even a little bit better. Okay, good. So this is a nice connection, and the way we're going to show that you could always solve a Pell's equation, no matter what d is, so you can always find a positive integer solution, is to reverse this. We're going to use the existence of good rational approximations to find a solution to Pell's equation. So to do that, we're going to need really just one tool. One logical tool, and it's a pretty simple one. But sometimes the simple tools are the best ones and worth stating carefully. And so this is called the pigeonhole principle. So the pigeonhole principle says if I put n plus 1 pigeons into n pigeonholes, I guess that was a thing once, then there's at least one pigeonhole with at least 2 pigeons in it. So for example, if I have 9 pigeonholes and 10 pigeons, if I try to put my pigeons in my pigeonholes, I'm going to have one pigeonhole with 2 pigeons in it. No matter how I try to do it, I'm going to have one pigeonhole that always has to have at least 2 pigeons in it. There's just not room to put just one in each. Okay, so this is a very, very powerful idea. We're also going to use the following infinite variant, which is if I have infinitely many pigeons, or only finitely many pigeonholes, then one pigeonhole holds finite. Then one of my pigeonholes has to hold infinitely many pigeons. So I mean, because if you have finitely many holes and finitely many pigeons in each pigeonhole, then you only have finitely many pigeons. Okay, so it's a little bit ridiculous of pigeons, but nonetheless, this is what we call it. And we're going to use this 3 or 4 times in the rest of the lecture. So let's see how that goes. So the first thing we're going to do with it is show Dirichlet's approximation principle. And this says if you have an irrational number alpha, then there are infinitely many pairs x and y of positive integers, such that when I form the fraction x over y, and I subtract alpha, the result is smaller than 1 over y squared. So this says x over y approximates alpha to within 1 over y squared. Another way you can say that is you have a fraction approximates alpha to within the square of its denominator. So this is, and as we saw, this is pretty good. I mean, somehow 99 over 70 works a lot better than the decimal approximation. Somehow takes less information than the decimal approximation to write. Okay. Okay, so how do we see this? Well, we're gonna use the pigeonhole principle. So what are my pigeons and what are my holes? So my pigeonhole, I'm gonna fix some integer, positive integer, n, which is larger than 0. And then I'm gonna subdivide the interval from 0 to 1 into intervals of size 1 over n. So subdivide 0n into, the interval from 0 to 1 into intervals of length 1 over n. So each of those intervals of length 1 over n, that gives me one of my pigeonholes. So just for example, n was 3, I just chop it like this. So I have 3 holes sitting on the unit interval. And my pigeons, well, I'm going to take the multiples of my irrational number alpha from 0, so from 0 times alpha up to n times alpha. So since I'm going from 0 to n, this is n plus 1. So 10 pigeonholes and n plus 1 pigeons. But I don't just take these multiples, I take their fractional part. So this is sort of like the part after the decimal point. Sort of concretely, sort of brackets beta, if beta is just some positive rational or some positive real number, means you take beta and you subtract off sort of its integer part, and that's the fractional part. So in particular, these fractional parts are numbers between, but this is the part that comes after the decimal point. So it's sort of a number between 0 and 1. So sort of these are pigeons, sort of each of them sort of, so each of these sort of goes onto the unit interval between 0 and 1. And then sort of depending on where it falls in the unit interval, it falls in sort of one of my subintervals, so into one of my pigeonholes. And since I have n plus 1 of these pigeons and only n holes, one of these pigeonholes, one of these sort of small intervals of length 1 over n, picks up 2 of these numbers, 2 of these fractional parts. And that sort of using that, I'm going to get a good approximation of alpha. So how? So just to write out what I just said, that means there's some pigeonhole. So there's some k between 0 and n minus 1, such that when I look at the interval from k minus 1 over n to k over n, I can find sort of 2 multiples, so 2 distinct multiples, I and j, of alpha, so like I times alpha and j times alpha, such that their fractional parts are both inside of this interval of length n. So let's see what that gives us. I mean, remember, my goal is to sort of produce some fraction approximating alpha. So let me just start by looking at j minus I, so these 2 indices, where the multiples both lie in this, where the fractional part of the multiples both lie in this interval. So we're looking at j minus I times alpha. So that's j times alpha minus I times alpha. And if I sort of just write j times alpha and I times alpha as sort of the sum, so like any number is the sum of its sort of integer part and its fractional part. So I'm just expanding that out. And then I get sort of the integer part of j times alpha minus the integer part of I times alpha, plus the fractional part of j times alpha minus the fractional part of I times alpha. And so this is the part that sort of I can control using that these are both in the same interval. And then this is an integer. So if I sort of rewrite this equation, so I'm going to divide by j minus I get alpha is equal to sort of now this sort of fraction, like where the top numerator and denominator are both integers, plus something that I can sort of try and control how big it is using that these are in the same sort of interval of length 1 over n. So really, so I have alpha is equal to x over y. So x is this integer up here, and then y is j minus I. Then epsilon sort of plus some sort of small number epsilon, and epsilon is the difference of the fractional parts over j minus I. So in particular, my y here is j minus I. Okay, so this is supposed to be my approximation. So I have to show that epsilon has absolute value less than 1 over y squared. Like that's what I'm trying to show in this Dirichlet approximation principle. But I can just write that out. So if I look at the absolute value of epsilon, well, that's the absolute value of the numerator over the denominator. The denominator is positive already. And since both the fractional part of j times alpha and the fractional part of I times alpha lie in the same interval of length 1 over n, they can be at most 1 over n apart. So this numerator is less than 1 over n. And then j minus I, well, j and I are both between 0 and n. So j minus I is less than, okay, sorry, j minus I is this is y. So I just sort of do this and I get sort of less than 1 over n over y. And then, so I simplify that, so I have something less than 1 over ny. And then now I want to use this sort of j minus I. Well, I and j are both between 0 and n, so j minus I is less than n. So this is, shoot, what did I do wrong here? Yeah, sorry. I said I was about to say something backwards. So sort of n is larger than j minus I is the point. So when I divide by n, I get sort of something smaller. When I divide by ny, I get something smaller than when I divide by just y squared. So here I just use that sort of n is greater than j minus I. That's just because j minus I, j and I are both between 0 and n. Okay, good. So then I really get my estimate. Good. So, and that sort of finishes the proof of the pigeonhole principle, or sorry, of Dirichlet's approximation principle. The proof used the pigeonhole principle to sort of get these sort of two fractional parts of multiples in this small interval. Okay. So now let's explain the existence of solutions to Pell's equation. So if I look at sort of not the statement of the Dirichlet principle, but sort of just this part of the proof at the end, sort of before I sort of simplify this sort of ny and just replace it with 1 over y squared to get sort of a nice statement of the approximation principle. So if I look just up to this part, then what I see is that for any n, I can find sort of positive integers x less than square root of n times square root of d and y less than or equal to n, such that the absolute value of x minus y squared root of d is less than 1 over n. So if you sort of, you'll see this if you just sort of follow through the proof of Dirichlet. Good. So if I have such a thing, well, then I can take its norm. So the norm of sort of x plus y squared root of d. And what I get is x plus y squared root of d times x minus y squared root of d. Well, the top, well, x is sort of at most n squared root of d and y is at most n. So this top is at most 2n squared root of d. And then, sorry, this left thing, and then this thing on the right, well, up here, it's sort of at most n, if I take its absolute value. And so putting that together, these n's cancel, and I just get that the norm of this thing is less than 2 times the square root of d. Okay. So sort of importantly, like sort of how this thing sort of x and y depended on n, little n, which I could take sort of bigger and bigger, but sort of how big the norm could be ended up sort of depended only, like didn't depend on n, it only depended on d. So because of that, sort of, that means I have infinitely many integers now. So I have infinitely many choices of x and y, such that the norm of x plus y squared of d is less than 2 squared of d. But then I can apply the pigeonhole principle. So, I mean, there are only finitely many numbers between, like positive integers less than 2 squared of d. Whereas here I sort of infinitely many of these guys that give me a norm in that range. So one of those pigeonholes now sort of, if I use this infinite variant, one of those pigeonholes must have infinitely many pigeons. So that means concretely, I can find some m that's less than 2 times the square root of d, such that this equation norm of x plus y squared of d equals m has infinitely many positive integer solutions x and y. So this is from the pigeonhole principle. Okay, and then this helps because what I want is one with norm 1. Like that's what I'm trying to find. I'm trying to find x and y where I have norm 1, because that gives me a solution of Pell's equation. But so I didn't quite get there. I just sort of found two different ones of sort of small norm, or sort of infinitely many different ones of small norm. But in particular, if I sort of take 2 of those, I sort of compute the norm of their quotient. Well, norms multiply, so I just get 1. I get m over m, and so I get 1. Okay, good. So on the other hand, if I sort of write out sort of this quotient, well, it works just sort of like, and it works just like the Gaussian integers. So you sort of do the like dividing by x2 plus y2 squared of d is the same as multiplying by x2 minus y2 squared of d, and then dividing by the norm of it. But the norm is just m. So I get sort of this guy. And then if I expand this out, well, I just get sort of these 2 equations. And I mean, I'm trying to get something sort of where the coefficients, so this guy and this guy, are both integers. So I want these two numbers to be, which a priori are just rational numbers now. I want these to be integers. And if these are integers, then I have something whose norm is equal to 1. And so then I'm done. These aren't always going to be integers, but I can apply the pigeonhole principle again. So if I sort of apply, for any of two of these, I get this, but for any two, but I have sort of infinitely many choices. Because I have infinitely many positive integer solutions. They give me norm of x plus y squared of d is equal to m. So in particular, I can use the pigeonhole principle to assume to take that sort of the two solutions I'm taking here, x1, y1 and x2, y2, satisfy that x1 is congruent to x2 mod m and y1 is congruent to y2 mod m. So here my pigeonholes are just sort of all of the pairs AB in Z mod MZ. And I just sort of look at what X is congruent to and Y is congruent to. And sort of since I have infinitely many possibilities for X and Y, for the pairs X and Y, so one of these pigeonholes has infinitely many elements in it. In particular, one of these pigeonholes has two different pairs in it. And so if I take my sort of X1, so if I take my sort of my pigeons in the same pigeonhole, so I take my x1, so it'd be congruent to x2 and my y1 be congruent to y2, then these really become integers. So I just need to show that the numerator, just like a computation we did when we were talking about sort of descent, I just need to show that the numerator is congruent to 0 mod m on both of these. But if I sort of just simplify using this congruence, like the first numerator becomes x1, x2 minus y1, y2 d, just becomes x1 squared minus y1 squared d. But I know sort of by somehow the other thing we sort of knew about these x1, y1, they give you x1 squared minus y1 squared d was equal to m. So in particular, it's sort of divisible by m. So this is congruent to 0 mod m. And then for the second one, just y1 x2 minus x1 y2, well, when we work mod m, this becomes y1 x1 minus x1 y1. These are the same thing, so I just get 0 mod m again. So really sort of once I sort of use this last pigeonhole, I sort of these really become integers, and then you're done. You've sort of found your solution to Pell's equation. Okay, so that's where we're going to stop. What I sort of haven't told you is how to actually find the first solution. So like in the few examples we've done, we've seen that sort of like in the few examples we've done, the first solution was pretty small, and so you could just find it by guess and check, for example, or by sort of in some of the examples, like we sort of used square triangular numbers. Then we sort of had some different way to think of it that let us found the first example, like the first solution to Pell's equation. So it's the smallest solution to Pell's equation. Once you sort of start writing down sort of larger d, and you don't even have to go that big, like the first solution actually sort of starts to get very, very big, or potentially very, very big. So we're not going to talk about this in class, but I just wanted to sort of point that out and say there's a beautiful connection and sort of a beautiful way to sort of find the first solution using the theory of continued fractions. So sort of going all the way back to sort of this continued fraction interpretation of the Euclidean algorithm and sort of the periodicity of continued fractions when you do square roots and quadratic numbers, sort of connects up with all these things. And you can really sort of give some nice interpretation in terms of a continued fraction for finding the first solution to Pell's equation. So we're not going to talk about this at all, but there's a little bit about this in one of the exercises on the worksheet, and there's sort of a section in the textbook about this if you'd like to learn more about how you can actually find this first solution. Okay, thanks everybody, and I will see you on Thursday.